All right, let's take a look at chapter 21, comparing two means. In chapter 21, we cover two sample problems, comparing two population means, two sample t procedures, using technology, robustness, details of the t approximation, avoid the pooled two sampled t procedures, avoid inference about standard deviations, permutation test. Two sample problems. A two-sample problem can arise from a randomized comparative experiment that randomly divides subjects into two groups and exposes each group to a different treatment. Comparing random samples separately selected from two populations is also a two-sample problem. Unlike the matched pairs design studied earlier, there are no matching of the individuals in the two samples. The two samples are assumed to be independent and can be of different sizes. The most common goal of inference is to compare the average or typical responses in the two populations. Comparing two population means. Conditions for inference comparing two means. We have two SRSs from two distinct populations. The samples are independent. That is, one sample has no influence on the other. We measure the sample response variable for both samples. Both populations are normally distributed. The mean and standard deviation of the populations are known. In practice, it is enough that the distributions have similar shapes and that the data have no strong outliers. Call the variable x1 in the first population and x2 in the second, because the variable may have different distributions in these two populations. Here is how we describe the two populations. Population 1, variable x1, mu, mean mu sub 1, standard deviation sigma sub 1. Population 2, variable sub 2, mean mu sub 2, standard deviation sigma sub 2. Subs for subscript. Comparing two population means. Here is how we describe two samples. Population 1 has a sample size in subscript 1, sample mean of x bar subscript 1, sample standard deviation of s sub 1. Population 2 has a sample size in subscript 2, sample mean x bar subscript 2, sample standard deviation s subscript 2. To do inference about the difference, which is mu1 minus mu2, between the means of two populations, we start from the difference x bar minus x bar. So x bar of sample 1 minus the x bar of sample 2, between the means of the two samples. Two sample t procedures. To take variation into account, we would like to standardize the observed differences between sample 1 and sample 2 means by subtracting its mean, mu1 minus mu2, and dividing the result by its standard deviation. This standard deviation of the difference in sample means is the quantity sigma 1 squared divided by n1 plus sigma 2 squared divided by n2, all square rooted. Because we do not know the population standard deviations, we estimate them by sample standard deviations from our two samples. The result is the standard error, or estimated standard deviation of the difference in sample means, which is labeled SE subscript, the difference between x1 and x2. So x bar 1 minus x bar 2 in the subscript for SE. as a reminder that it's the standard error for the difference of the sample means, which equals the square root of the quantity S1 squared divided by N1 plus S2 squared divided by N2. When we standardize the estimate, by subtracting its mean, mu1 minus mu2, and dividing the result by its standard deviation, the result is the two-sample t-statistic, where t equals the difference in the sample means minus the difference in the population means, divided by the standard error, or the difference. The two-sample t-statistic has approximately a t-distribution. It does not have exactly a t-distribution, even if the populations are both exactly normal. In practice, however, the approximation is very accurate. There are two particular options for using the two-sample t procedure. Two practical options for using the two-sample t procedure. Option 1, with software, use the statistic t with accurate critical values from the approximating t distribution. Option 2, without software, use the statistic t with critical values from the t distribution with degrees of freedom equal to or smaller than equal to the smaller of N1 minus 1 and N2 minus 1. So take the two sample sizes and subtract 1. Look at the degrees of freedom for each sample and use the smaller degree of freedom. The significance test gives a p-value equal to or greater than the true p-value. Two sample t procedures. Draw an SRS of size N1 from a large normal population with unknown mean mu1 and draw an independent SRS of size N2 from another large normal population with unknown mean mu2. A level C confidence interval for the difference between the population means is given by the difference between the sample means plus or minus your critical t-score times your standard error for the difference of your sample means. Here, t star is the critical value for confidence level C for the t distribution with degrees of freedom from either option 1 software or option 2 the smaller of N1 minus 1 and N2 minus 1. The two sample t procedure to test the hypothesis of H naught that mu1 equals mu2, calculate the two sample t statistic, which is t equals x1 minus x2, because if we then subtract the difference in the population means, that's 0 here. So we discard that portion. So just the difference in the sample means divided by the standard error for the difference in the sample means. Find p-values from the t distribution with degrees of freedom from either option 1, the software, or option 2, the smaller of N1 minus 1 and N2 minus 1. Example, we're going to state, plan, solve, and conclude. People gain weight when they take in more energy from food than they expend. James Levine and his collaborators at the Mayo Clinic investigated the link between obesity and energy spent on daily activity with data from a study with N1 equal N2, which were both 10 health volunteers, 10 who were lean, 10 who were mildly obese, but still healthy. They wanted to address the question, Do lean and obese people differ in the average time they spend standing and walking? What's our plan? Give a 90% confidence interval for the difference between the population means. The difference in average daily minutes spent standing and walking between lean and mildly obese adults. To solve, well, our examination of the data reveals all conditions for inference can be at least reasonably assumed. The distributions are a bit irregular, but with only 10 observations, this is to be expected. And to solve it, the descriptive statistics yielded that your group 1 was the lean group and your group 2 was the obese group. There were 10 people in each group. The mean for the lean group was 525.751, and the mean for the obese group was 373.269. The standard deviation for the lean group was 107.121, and the standard deviation for the obese group was 67.498. For using option 2, conservative degrees of freedom in absence of technology, N1 minus 1 and N2 minus 1 are both 9, and T star is 1.833 from our table then, giving us a confidence interval of the difference in the sample means plus or minus our critical T plus the times the standard error for the difference in the sample means, which ends up being 152.482 plus or minus 73.390, or 79.09 to 225.87 minutes. Software using option 1 gives the degrees of freedom to be 15.174 and T star to be 1.752 for a confidence interval of 82.35 to 222.62 minutes. Narrower because option 2 is conservative. The option we chose is conservative. Conclude, whichever interval we report, we are at least 90% confident that the mean difference in average daily minutes spent standing and walking between lean and mildly obese adults lies in this interval. So if we did method 1, we report method 1's interval. If we did method 2, we report method 2's interval. Community service and attachment to friends. State, plan, solve, conclude. Do college students who have volunteered for community service work differ from those who have not? A study obtained data from 57 students who had done service work and 17 had not. One of the response variables was a measure of attachments to friends. Here are the results. Group 1 had some community service. There were 57 at an average of 105.32 hours and a standard deviation of 14.68. Where the second group is the non-community service group with 17 individuals with an average of 96.82 and a standard deviation of 14.26 hours. Our plan, the investigator had no specific direction for the difference in mind before looking at the data. So the alternative is two-sided. We will test the following hypotheses. That the null hypothesis is that there is no difference between mu1 and mu2. Mu1 is mu2. And our alternative hypothesis is that there is a difference between mu1 and mu2, that they are not the same, not equal, two-sided. The two-sample T statistic is T equals the difference in the sample means divided by the standard error for the difference in the sample means, which is 2.142. Software option 1 says that the two-sided p-value is 0.0414. For using option 2, N1 minus 1 is 56, N2 minus 1 is 16. Therefore, comparing our test statistic of 2.142 to two-sided critical values of a t with degrees of freedom 16 distribution, Table C shows the p-value is between 0.05 and 0.04. Conclude, the data gives a moderately strong evidence, p less than 0.05, that students who have engaged in community service are, on average, more attached to their friends. Using technology, we've got Crunchit and we've got the two sample t-test in the TI 83 plus. Crunchit and the calculator get option 1 completely right. The accurate approximation uses the t distribution with approximately 15.174 for degrees of freedom. Crunchit rounds this to 15.17 degrees of freedom. The p-value is p equals 0.0008. It's very small. Minitab uses option 1, but truncates the exact degrees of freedom to the next smaller whole number to get critical values and p-values. In this example, the exact degree of freedom, which is 15.174, is truncated to degree of freedom 15, so that Minitab's result are slightly conservative. That is, Minitab's p-value rounded to p equals 0.001, and the output is slightly larger than the full option 1 p-value. Excel rounds the exact degrees of freedom to the nearest whole number so that the degrees freedom 15.174 becomes degrees freedom 15. Excel's method agrees with Minitab's in this example, but when rounding moves the degrees of freedom up to the next higher whole number, Excel's p-values are slightly smaller than is correct. This is misleading. Another illustration of the fact that Excel is substandard as statistical software. The two sample t procedure are more robust than the one sample t method, particularly when the distributions are not symmetric. When the sizes of the two samples are equal and the two populations being compared have distributions with similar shapes, probability values from the t-table are quite accurate from a broad range of distributions. When the sample sizes are as small as n equals 1 equals n sub 1 equals n sub 2 equals 5. So in two samples as small as 5. When the two population distributions have different shapes, larger samples are needed. As a guide to practice, adapt the guidelines for one sample t procedures to two sample procedures by replacing sample size with the sum of the sample sizes N1 plus N2. Caution, in planning a two-sample study, choose equal sample sizes whenever possible. The two-sample t procedure are most robust against non-normality in this case, and the conservative option 2 probability values are most accurate. The exact distribution of the two sample t statistic is not a t distribution. The distribution changes as the unknown population standard deviation changes. However, an excellent approximation is available. Approximate distribution of the two sample t statistic. The distribution of the two sample t statistic is very close to the t distribution with degrees of freedom given by the square of the standard error for the difference in the means divided by 1 over n minus 1 times the quantity S1 squared over N1 quantity squared plus 1 divided by n sub 2 minus 1 times S2 squared divided by N2 squared. This approximation is accurate when both sample sizes N1 and N2 are 5 or larger. So to get an approximate difference, degrees of freedom. Avoid the pooled two-sample t-procedures. Many calculators and software packages offer a choice of two-sample t-statistics. One is often labeled for unequal variances, the other for equal variances. The unequal variance procedure is our two-sample t. Never use the pooled t procedure if you have software or technology that will implement the unequal variance procedure. There are methods for inference about the standard deviation of normal population. The most common such method is the F-test for comparing the standard deviations of two normal populations. Unlike the T procedures for means, the F-test for standard deviations is extremely sensitive to non-normal distributions. We do not recommend trying to do inference about population standard deviations in basic statistical practice. As an alternative to two-sample t-tests, in some instances, it may be to our advantage to perform a permutation test in general. If experimental units are assigned to two treatment groups completely at random and our null hypothesis is no treatment effect, we can test hypothesis using sample means as follows. First, list all possible ways units can be assigned to treatment groups. Second, based on the data obtained for each possible assignment, determine what the difference in means mean for treatment 1 minus mean for treatment 2 would be. Under the null hypothesis, each of these is equally likely. Permutation tests method continued. Third, determine the distribution of these possible outcomes by listing all the different possible mean differences and their corresponding probabilities. This can also be represented by a histogram. Using this sampling distribution, determine the p-value of the actual mean difference you obtain. The resulting sampling distribution of outcomes is called the permutation distribution. Practical issues. First, unless the number of ways units can be assigned is sufficiently large, the smallest possible p-value may not be very small. Second, listing all possible outcomes can be tedious. Third, permutation method is most likely to be useful with small to moderate size experiments because of the robustness of T procedures.